Hello. So this is also joint work with Christian Sutler, and it's work in progress, but if it doesn't appear soon on the archive, you can start throwing rocks at me. Um, so speaking of things that haven't appeared on the archive, maybe you saw my hottest talk over a year ago now. Christian and I we've been thinking about models of cubical type theory and whether these models sort of correspond to ordinary spaces or not. And Christian had this argument a while back that many of these model structures don't present spaces, and so we wanted to write down this argument. And somewhere in the middle of it, there's this funny lemma, and I can't really motivate it here because I'm talking about something else, but I want to kind of explain how I ended up here. Um, if you are in some cubical model that's chosen well, and you choose well some n, you look at n cubes quotiented by a certain automorphism, then exponentiation by that weird object preserves the trivial cofibrations. And these trivial cofibrations are supposed to be maps that are kind of built out of open box inclusions. And so we saw some kind of, well, whatever. Okay, so that's something that we needed. And there's kind of a usual strategy for proving these things. You want to start out by checking it for these generating trivial cofibrations, these open box inclusions. If I take an open box inclusion and exponentiate it by this weird object, I still have a trivial cofibration. And then I extend that from the generating case to all my trivial cofibrations by one of two routes. So if this operation that I'm doing is a left adjoint, then there's a very simple kind of moving back and forth way to extend it from generators to all trivial cofibrations. But it happens that we're not in this situation. This funny thing is not a left adjoint. And so the other way to do it is to use a kind of characterization of the trivial cofibrations as cell complexes or relative cell complexes, which are built out of the generators by certain colimit looking operations. And this sort of stuff goes under the name of small object argument. But are we actually in a situation to use the small object argument? Well, it turns out that we're not quite, for two reasons. And well, one reason is that we would kind of like to do these things constructively. And the small object argument is less applicable constructively than it is classically. But actually, we're also interested in examples of these cubical style model structures, which even classically we think are not generated by this argument. So that's kind of the background of how I ended up here. Now I want to kind of go back and kind of explain some background in more detail here. But the theme of this talk is taking things that classically we would sort of treat as properties and treating them as structures. So I think that this is kind of an impact of homotopy type theory and constructively minded people coming into this homotopy theory sphere, is that we have to kind of rethink things structurally to avoid, making choices and so on. And so maybe that's why this might be interesting to you in general. Okay, so let's go back to the beginning. This whole thing is going to be about weak factorization systems. In a weak factorization system on a category is a pair of classes of maps, which we call the left and right classes, such that they are, one, characterized by a kind of lifting property against each other. So whenever I have a square like this with a left map on the left and a right map on the right, I get a diagonal lift in the middle. And moreover, the left and right maps are completely characterized by having this property against each other. And second of all, I can always factor an arbitrary map into a left map followed by a right map. And these things appear all over the place in the world. So in a lot of categories, you have a weak factorization system of complemented monomorphisms against split epimorphisms. One that's relevant to HOTS and to homotopy theory is the confibration factorization system in simplicial sets. And in cubical sets, we in the HOT world are interested in this uniform confibration factorization system. So we'll see a bit more of those later. Now, in the wild, a lot of weak factorization systems are generated by a set of left maps. So that means that if I want to test if something is in the right class, I don't have to test whether it lifts against everything in my left class. I can just test if it lifts against these maps in this small set S, which will be a subset of L. So for example, one of these complemented monomorphism split epimorphisms factorization systems, the one in the category of sets, is generated by just one map, the map from the empty set into the one element set. So when is something a split epimorphism, when for everything in the codomain, I can pick something in the domain that maps to it. And in simplicial sets, this confibration factorization system is generated by the set of Horn inclusions. So the inclusion, for example, of this cone into the triangle. Okay. But there's actually a more general concept than being generated by a set, which is being generated by a category. So this covers more examples of weak factorization systems. Set generated one. And what does it mean to lift against a category? Really, by a category, I mean a diagram. So I have some category, small category J, and a functor from that into the arrow category of the category I'm interested in. And I say that something has the right lifting property against this diagram if, first of all, for every object, every uj, I can find a lift for f against it for every lifting problem. But also, I can choose these lifts in such a way that whenever I have a morphism coming from this diagram, the lifts agree. So they make this triangle made out of the dash maps commute. So I've tried to choose some examples that are generated by a category, but not generated by a set. And a known example is the complemented monomorphism split epimorphism factorization in abelian groups. So it's generated by some funny category whose objects are these two maps. And again, the one that's interesting to me is this uniform confibration factorization system in cubical sets. Okay, so let me go into a little more detail on that one, just so we have some anchor for ourselves. So this factorization system is generated by some kind of open box inclusion. So we have some kind of choice of particular sub-objects of cubes we're interested in. And we say we want, whenever we have one of these sub-objects of a particular form and a point, either 0 or 1, we want to be able to lift against some kind of open box, which is built out of this sub-object. And then we don't just want a choice of lifts for each of these objects, but whenever we have a pullback square of sub-objects of our specified kind, we put this in as a coherence that we want to require against our choice of lifts. Okay, so this is not constructively generated by a set. This factorization system is generated by this category. And even classically, for some choices of allowable sub-objects, we're pretty sure that it's not generated by a set. Okay. So as you've probably detected from the way I'm talking about these things, we usually don't start from a factorization system and then recognize it's generated by something. We start from a set of things that we want to lift against, and then we generate the factorization system. And so we can always kind of come up with the classes of maps that we want to have. We start with our generators S. Let's say we're generating from a set. We say our right class are things that lift against this, and our left class are things that lift against our right class. So first start with a set, define the right class, define the left class for that. But we haven't got a factorization system. We need to define the factorizations as well. And so this is where the small object argument comes in. The small in the name is, in order to apply it, we need to know that this set of generators is small, whatever that means. So if S is small enough and our category is well behaved enough, we can use one of these small object arguments to build our factorizations. So the original one is due to Daniel Quillen. Quillen's small object argument is for generating a factorization system from a set, assuming some stuff. And I can kind of sketch for you how it works. We start with a map. We want to factorize it as a left map followed by a right map. And we know that right maps are the things which lift against the maps in this set of generators. So what we're going to do is try to put into X solutions for all these lifting problems. So let's suppose we're doing the simplicial set case, so our generators have horn inclusions. We look for all the horns in X that should be filled, and we glue on triangles filling in those horns. That gives us a new simplicial set, X1, and that one has still a map down to Y because all those triangles exist in Y. And we can keep doing this because we have maybe created some new problems to be solved. And if we go on for long enough, eventually this map down to y becomes a right map. This process doesn't ever actually stop, but we can cut it up at some point. And it turns out that this map from x to x kappa will be a left map, and so that's our factorization. And now going back to my story from the beginning, one thing we notice about the way this factorization is constructed is that the left factor of our factorization is what's called the cell complex. So it's built up in a certain way, starting from the generators, as a transfinite composite, the horizontal line, of a bunch of pushouts, which I call co-base changes for some reason, of co-products of generators. And then there's something we can conclude by something called the retract arguments, that not only are these left vector cell complexes, but any left map at all is going to be a retract of one of these cell complexes in the arrow category. Okay. And that's the kind of thing that we wanted to exploit back in our story. So one way to exploit it is by formulating it in the following way. You can say that an arbitrary class of maps in a category is saturated when it's closed under all these operations. And it happens to be the case that the left class of any weak factorization system is saturated. So as a consequence, if we generate a factorization system from the small object argument, then its left class is the least saturated class containing S. And then we can use it to prove the kind of things like in my beginning story. So if I have a functor and I know it preserves these operations, and I want to check that it preserves left maps, then it suffices to check that it sends the generators left maps. Because I can define the kind of pre-image of the left maps under F, check that this is a saturated class and contains the generators, and that will do that. But we're in a case where we're not generated by a set. So what we want is an equivalent of this kind of process for generation by a category. And for that, we can't use Quillen's small object argument, but we can use something that exists, which is Garner's algebraic small object argument. So this is a operation or construction for building a weak factorization system from a diagram. And it has some advantages over Quillen's argument, besides being more general. So one is Quillen's thing is kind of ad hoc. This factors through a very standard free monad construction. And it also produces something which is called an algebraic weak factorization system. So going with my first slide theme, this is a kind of more structured version. In the classical homotopy theory situation, we have two classes of maps, but now we're going to be looking at structures. So first of all, we have a functorial factorization. So we have two functors, L and R, that produce the left and right halves of our factorization. But moreover, let's look at this right functor. This right functor is going to be a monad whose unit is given by the square, which happens to have the other functor L in there. And the right maps of the factorization system correspond to algebras for actually the underlying pointed endofunctor of this monad for whatever reason. But notice that's a structure. So we can say what it means for a map to have a right structure. We don't just talk about things being right maps. And dually, this L is going to be a comonad, whatever. Okay. So how does the algebraic small object argument work? Well, like Quillen's argument, it kind of breaks up into steps. So there's some kind of operation that we want to apply again and again until we converge. And the thing we do for the one step makes use of this construction called the density comonad, which I always call the codensity monad by accident. What this does in the context of the algebraic small object argument is take a map, so it's a functor from the arrow category to the arrow category, and returns a kind of amalgamation of all the possible lifting problems we could have from the left against this. So it's that co-limit there. We look for all the squares from an arbitrary u, that should be a j, uj to f, and glom them all together. And this thing also has a kind of canonical lifting problem against f, which is the co-unit of the comonad. And now the kind of one-step factorization of f is the push-out gap map of the square. So that's that. This operation, which sends f to f1, defines a pointed endofunctor of the arrow category. And I want to remark that when we're generating something by a set, this co-limit just reduces to a coproduct, and this density comonad thing applied to F just gives us a coproduct of generators. So that's much like the set generation situation we had in the equivalence argument. So this is our one-step thing, and then we want to iterate it. We want to take the free monad. Our R is going to be the free monad on this pointed endofunctor. Unfortunately for us, we don't have to figure out how to make free monads because Kelly wrote this paper with a very scary name that does it for us. And I'm not going to go into details on that, but let's just say that given a pointed endofunctor on some category, this construction builds a free monad using some operations that we like, pushouts and these transfinite compositions or sequential colimits. And I want to kind of give some intuition for what's happening in the algebraic small object argument compared to Quillen's argument. Like in Quillen's argument, we're repeatedly adding in solutions to lifting problems that we find, but we're also quotienting out when we add a solution twice. So in Quillen's argument, we might add, in fact, we do add solutions to the same problem again and again and again, but we quotient that out when we do the algebraic small object argument. So summarizing what just happened, we started from the generators, we built this density comonad thing, we use that to define the one-step factorization system, and then we iterate the one-step factorization system in a good way to build this monad R. And the unit of that monad R contains this left part of the factorization system, which is actually what I'm interested in. Okay, so can I describe this thing, this left factor that I get out as a cell complex in the way that I can for Quillen's argument? Well, it does actually build that left factor as a transfinite composite. I didn't show you the details, but it's true. But these step maps are not left maps necessarily, like they are in Quillen's. The problem is this collapsing out of duplicated solutions kind of screws things up. Now, it turns out to be important for our application that you can constrain these a bit. So, for example, in our applications, they turn out to be monomorphisms, but they're not even necessarily cofibrations. And the problem is this funny condition that I won't explain at all, which you need to hold for those. So we were kind of wondering what to do here, but eventually we had the idea to not look at these step maps at all, but look at the maps from the starting point to the point that you're at, to your kind of alpha step in your factorization. And if you look at those maps and put them next to each other in a row, you get this diagram in the arrow category. And it turns out that those maps are always left maps. And moreover, they are equipped with L algebra structures such that this diagram is a diagram in the category of L algebras. So those squares are morphisms of algebras. And once we had that idea, we started to see the pattern. So this left factor is actually built by colimits in this coalgebra category, which looks similar to the colimits you see in Quillen's argument. So you have these sequential colimits, and then you have pushouts. And somehow this class of M we also care about. And the other thing you need to be able to do is compose left algebra structures. Okay. Right, so you do those things, and where you're starting from is from the coalgebras that come from this density comonad. So the density comonad factors through the forgetful functor from the L coalgebra. So those things are always left maps in a canonical way. And so that seems to be a cell complex description of what we get out of this argument. Now we want to kind of sum that up in a universal property like this saturation property we had. We want the L coalgebras to be the smallest things which have these structures in them. And like I said, there's composition occurring among these operations. So it's not really convenient to talk about the category of coalgebras, which doesn't see this composition structure, but look at what Bork and Garner came up with as a way of looking at these things, a double categorical perspective. So a double category is basically just a category where you have two kinds of maps. One you think of as going horizontally and one vertically. And so for us, we have this double category of coalgebras where the objects are just objects in our category. Horizontal morphisms are regular morphisms, but vertical morphisms are morphisms equipped with a coalgebra structure. And the squares are morphisms of coalgebras. So we've got this particular one for coalgebras for our left maps. But we can kind of abstract that situation and call anything that looks like this in the right sort of way a vertical structure on the category. And then our theorem is, well, if you fix a diagram for which the algebraic small object argument applies, and this class M. And you have some vertical structure which has all these constructions in it, and also something called the left connection. Then anytime you can lift the density comonad through the category of vertical morphisms of this thing, you can also lift the left vector functor through the same thing. And there's even some structure you can impose on this thing that makes it essentially unique. So it's some kind of universal property. And this is telling me that if I can give every generating local algebra an A structure functorial way, then I can give actually anything spit out by my vectorizer one of those structures. So, of course, the usefulness of this thing depends on whether we can analyze this density comonad, this generator thing, in a useful way, but it turns out that we can, at least in the case we're interested in for uniform fibrations. So applying the density comonad turns out to spit out some kind of open box looking thing or co-product of them. And that's the kind of reduction that we're looking for. And we can pick our A in a nice way that does what we want. It's maybe worthwhile to note that for some things it's useless. So sometimes the image of this density comonad already hits every map that we're interested in, so we haven't reduced anything at all. Okay, somebody's standing over there, so I'll just close out with a couple of remarks. One thing I would have liked to talk about is another application of this to building extension operations. So this is a kind of thing that says that if we have maybe a fibration over the domain of a map in a left pass, we can extend it in a nice way to something that lives over the codomain. And this is somehow important in building these cubical model structures. We usually use a universe for it, but for building model structures, I don't know, it kind of seems weird that we need to rely on universes. And we actually don't. For some cases, we can use this stuff to reduce the extension to the generating case where we know what to do. And for Quillen's small object argument, I also talked about retracts, and I seem to have forgot to talk about that in our case. There is something you can do, but you get this map and it's not really canonical, and we don't know whether there's a universal property that these things have. So if you're interested in what the problem is there, it's kind of easy to summarize, and I would be happy to talk about it. That's it.
We have time for one or two quick questions.
Thank you for the talk. So is there a conclusion about the beginning story about like quotienting cubes by symmetries?
Do you mean like, can we make this work?
Yeah. Right.
Yes, yeah. So this we can do. Basically, yeah, this was something that I glossed over quite quickly, but what you can do is you can define a double category which says things that when this exponentiation is applied become trivial cofibrations. And you can show that when this thing is applied to generators, they become trivial cofibrations. So then you check that notion of structure is closed under these colimits like transfinite composition and push out along things. It turns out that it is. That's something that has to be checked, which is a little involved to check. But then yes, yeah, it works.
Okay, thanks. So you have kind of characterization of the coalgebras for the co-pointed ender functor as the least class satisfying a list of conditions, or
not quite.
Okay.
So, I mean, what we have is that you have this kind of extension from you have this kind of universal property with L, you can call it. But okay, what do I want to say here? What I mean is, so this theorem is telling you something about the free coalgebras, the things that are spit out by L.
Okay.
So it gives you structures on those. Then if you want to say something about left maps in general are retracts of these things, right?
Okay.
Yeah.
So this talks about. Maybe we should just talk.
Well, I would be happy to talk to you. Yeah, but like what you're saying is something that I want, but because of some issues with the retract situation, I don't have it. And I would love to talk about it more with you.
Sure. Yeah.
Okay, there's coffee downstairs.